Okay, it's now time to review our last lesson for the unit lecture exam, and that is going to be lesson number 5 on linear momentum. So this is going to be chapter 6 out of your textbook. So what do we mean by linear momentum? So linear momentum is going to be given by lowercase letter p, and then it's going to be equal to the mass of an object and then multiplied by the speed of the object. So that is what we're going to define to be linear momentum. And so there could be a very simple question on the exam where you are given the mass of the object and you're given the speed of the object, and then you have to calculate the momentum of the object. Or if I give you the momentum of the object and I give you the mass of the object, you could find the speed of the object. So I've got to give you 2 of the 3 letters and then you can solve it. And then also look at the units. So the unit for mass is the kilogram, and then the unit for speed is the meter per second. So the units for momentum are going to be kilograms meters per second. So it doesn't really have a nice metric unit that goes with it. Okay, now what we want to do is relate momentum to force, which is going to be very important. So that you should now know that force, according to Newton's second law, is going to be equal to the mass of an object times its acceleration. So forces cause masses to accelerate. But if we write this in terms of momentum, you'll notice that it turns into the change in momentum over time. So a force causes the momentum of a system to change. So that's the version of Newton's second law as with respect to the momentum of a system. So forces change the momentum of a system. So what's the point here? Okay, so you should now know that if you know what the force is acting on a system, you could calculate its acceleration A. If you knew its acceleration A, you could use that to figure out its speed, and you could also use that to figure out how far it's going to go by using the how fast and the how far equations. So this time, if you know the force acting on a system, you're going to be able to predict the momentum of the system. And then once you got the momentum of the system, then again you can predict its motion. So this is just a different way of predicting the motion of a system. Okay, first one, application of this formula is, let's assume that there is no force acting on the system. So if no force is acting on the system, then F is going to be equal to 0. You can multiply both sides by T, which means it's still going to be 0. So you got 0 equals the change in momentum. And so you end up with that the momentum you start with has to equal the momentum you end with. That's conservation of momentum. So conservation of momentum is very, very useful in physics. So if there's no force acting on a system, momentum is going to be conserved. The momentum you start with has to equal the momentum that you end with. Now there's 3 applications of conservation of momentum. So let's take a look at them here. So the first one is going to be the explosion. So every single one of these three applications starts off the same way. So that we're going to start off with that the momentum initial before something happens has to equal the momentum afterwards. So momentum initial has to equal the momentum final. So all of these applications are going to start out the same way. Now the difference is that in the case of the explosion, you're going to start with one object, so it's going to have a certain momentum. So the initial momentum of that thing, and then it's going to blow apart. So when it blows apart, it's going to turn into two pieces. Now in actuality, it can turn into as many pieces as it wants. It's just that two pieces is easier to analyze than 100 pieces. So this time we're going to have P final for object number 1, and then you'll also have P final for object number 2. And now let's plug in. So instead of the letter P, we know that it's MV. Okay, and then over here we'll put MV, and then we'll put MV over here, but we need to put a lot of subscripts. So you notice that I put M total for the total mass that you start with. And then we have to have times the initial speed of the object, and then that's got to equal the momentum for this particle plus the momentum for this particle. So that's why there's so many different subscripts on it. Now, the good news is I've got to give you in the problem quite a bit of information in order to be able to solve that equation, because you see that it's got 1, 2, 3, 4, 5, 6 different letters. And in general, if you got one equation, you can have only one unknown that goes with it. So I'm going to have to give you quite a bit of information to solve one of those things. So for example, here you have a stick of dynamite that is stationary, and then it explodes. And then 0.5 kilograms of it travels to the right, and I give you the speed to the right. And then the question is to calculate the speed and the direction of the other piece. Well, you might think that I didn't give you enough information, but when I said the word stationary, then that meant that its initial speed is going to be 0, which means its initial momentum is going to be 0. Okay, then the other thing is I told you the mass of one of the pieces, but I didn't give you the mass of the other piece, because I told you what was the total mass, and I told you what was one of the pieces, so you should be able to subtract it to figure out what the other piece has got to be. And then you solve it for V. And then keep in mind the sign convention. So anytime that something is traveling to the right, give it a positive speed, and anytime that something's traveling to the left, give it a negative speed. This one turned out to have a negative speed, which meant that it was traveling to the left. Okay, then you can also have the inelastic collision, which is going to be the exact opposite of the explosion. So notice we start out exactly the same way. The initial momentum of the system has to equal the final momentum of the system. The difference this time is that you've got two pieces initially that are going to collide, and then when they collide, they're going to stick together. So notice it's this thing here, but it's flip-flop. So these two are on this side, this is on this side, but we set it up exactly the same way. So here's an example of how you would use the inelastic collision equation. So you have a 100-kilogram quarterback is running to the right at 8.9 meters per second. He's hit by a 150-kilogram linebacker traveling at 8 meters per second to the left. They then stick together what's going to be their final speed. So we start by saying their initial momentum has to equal their final momentum. The initial momentum of the quarterback and the tackler has to equal the momentum when they're all stuck together. Plug in all of our numbers and then solve it for the final speed. So that is case number 2. So case number 1 is going to be the explosion. Case number 2 is going to be the inelastic collision. And then case number 3 is going to be the elastic collision, where you've got two things that are going to crash into each other and then they're going to bounce off of each other. Now this is a perfect elastic collision, which means that when they collide, they're not going to give off any heat when that happens. So they're just going to collide and bounce off. And so this is going to be a perfectly elastic collision. We're going to start off by saying that the initial momentum of the system has to equal the final momentum of the system. But this time you'll have two initials, and then when they've collided and come apart, you're going to have two final momentums. And so here's an example of how you would use that equation. All right, let's take a break, and when we come back, we will continue our discussion of linear momentum.